Hello students, welcome back to your physics class. So today is your third lecture on simple harmonic oscillations. And today we will learn how to actually set up the differential equation for simple harmonic oscillators and solve it. So in order to set up the differential equation for a simple harmonic oscillator, we are basically going to use Newton's second law of motion. So as you all know, Newton's second law of motion basically tells us that the force acting on a body is equal to its mass into acceleration. So we are going to use this basic law of motion. So by Newton's second law of motion, force acting on a body is equal to its mass into acceleration, d2x dt2. And for a simple harmonic oscillator, as we have discussed in our previous lectures, that the force acting on the oscillator at every point of its motion is the restoring force, because the force tries to bring back the particle to its equilibrium position, and that force is directly proportionate to the displacement of the particle or its distance from the equilibrium position. Then if we choose to represent the displacement as x, the variable x we choose to represent the displacement of the particle, then the force acting on the particle, the restoring force, which by Newton's second law of motion is mass into acceleration, that is directly proportional to the displacement x, and there's a negative sign coming in because the force is directed opposite to the displacement. And when we rewrite this proportionality as an equation, we plug in the proportionality constant mu. So mu is nothing but the proportionality constant which we invoke to change this proportionality relation to an equation. So d2x dt2 is basically equal to minus mu by m into x. Okay, where m is of course the mass of the oscillator, and the constant mu by m, the proportionality constant mu divided by the constant mass m, that we depict by another constant omega square, that we are representing by another constant omega square. So d2x dt2 is equal to minus omega square x. Now omega would be the angular frequency of motion, but that we are not mentioning at this point. At this point we are just saying we are replacing this constant mu by m by another constant omega square, so that we get the resultant relation d2x dt2 plus omega square x is equal to 0. So this is a second order differential equation. In your bridge course, you have already learned about differential equations of various orders and degrees. And so you know this is a second order first degree differential equation. Second order, why? Because the highest order derivative is 2. And why first degree? Because the power of the highest order derivative d2x dt2, its power is 1. Okay. So we need to solve this second order differential equation. Now, maybe in your bridge course, you have learned a formal way of solving second order differential equations. So this is a homogeneous second order differential equation, as you see, because the power of x is same at on every term. This 0 term on the right, we can think of it to be 0 into x to the power 1. So the power of x is 1 everywhere. So it's a homogeneous second order differential equation, and you have learned maybe how to solve it using complementary function. But we are here going to solve it in a more innovative way. As you will see, we will solve it in two steps, two simple steps. First, we are going to reduce the second order differential equation to a first order differential equation, and then we are going to simply integrate the first order differential equation. So let's begin. So first, we are going to multiply this differential equation throughout by 2 dx dt. So throughout this differential equation, we are going to multiply by 2 dx dt into this equation. And let's see what we get by doing so. By doing so, we get this simple equation, equation 4, 2 dx dt into d2x dt2 plus 2 dx dt into omega square x is equal to 0. Okay. Now, if you look into this equation 4 carefully, you can see that the first term of this differential equation can be replaced by the first term of equation 5. Why? Because ddt of dx dt whole square, this term, if you break and take the differential, you will get 2 dx dt into d2x dt2, which is why this first term of equation 4 can be written as first term of equation 5. And again, if you look carefully, the second term of equation 4 can be written as the second term of equation 5, because ddt of x square is 2x dx dt. ddt of x square, if you take, it is 2x dx dt, which is why the second term of equation 4 is the same as second term of equation 5. Now, since this happens, we can rewrite equation 5 as ddt of dx dt whole square plus omega square x square is equal to 0. Okay. Taking the ddt outside, we can write it in this form. And since ddt of this term within the square bracket is 0, we can write the term within the square bracket to be a constant. And so we have the term within the square bracket is a constant c. Now, we are going to fix up the value of this constant c. We are going to find it out what it is equal to by using again our physical considerations. Okay. So when our particle is performing simple harmonic motion and when it is at one of the extreme positions, what happens? The particle moves to its extreme position from the equilibrium position. Then after moving to its extreme position, it turns back and comes back to its equilibrium position. So at the amplitude position or extreme position, the direction of motion of the particle is being changed. It is traveling in one direction while it's going from equilibrium to amplitude, but at amplitude its direction of motion is changing, which is why it's coming back to equilibrium. So at the extreme position, the direction of its velocity is changing as the particle is turning back and coming back to its equilibrium. So at the extreme position, for an instant, we can easily say that the velocity of the particle is going to 0 because its velocity is in a certain direction. Then when it reaches the amplitude, its velocity changes direction so that the particle can retrace its paths. And so since the velocity changes its direction at the extreme position, so for an instant the velocity goes to 0 at the extreme position. Okay. So when x is equal to a, amplitude or extreme position, then dx dt, the velocity at that instant of time, is 0. So we have put in that condition dx dt is equal to 0 at x is equal to plus minus a, because there can be two amplitude positions, plus a and minus a. At both positions the velocity turns instantly to 0 and the particle retraces its path and changes its direction of velocity. And so fitting this condition into this equation, equation 6, we see that we get c, the constant c, to be equal to omega square a square. Dx dt is equal to 0, so omega square a square is equal to c. And putting this in back into this equation, the equation can be rewritten as dx dt whole square plus omega square x square is equal to omega square a square, where the constant c is equal to omega square a square. So when we take this omega square x square to the RHS, we get dx dt whole square is equal to omega square into a square minus x square. So you see, the second order differential equation that we had is reduced to a first order differential equation. The differential equation becomes first order and second degree. Now we take square root of both sides of the equation, and doing that we get this relation dx dt is equal to plus minus omega into root of a square minus x square. So we are just taking root of both sides of the differential equation. And plus minus, of course, because we are taking the square root, we would consider only the positive sign for the moment. You can also consider the negative sign. You will just have a phase difference. Considering the positive sign, we get dx dt is equal to omega into root of a square minus x square. So bringing this to the all the x's to one side, we get dx by root of a square minus x square is equal to omega dt. And then what we do is we integrate both sides. Integrating both sides, we get the following relation. When we integrate 1 by root of a square minus x square, it gives us sine inverse x by a. And integrating the left hand side, we get omega t plus an integration constant delta. The integration constant we depict by the symbol delta. And so this gives us x is equal to a sine omega t plus delta, where a is of course the amplitude and delta we can easily see is the initial phase or epoch, because depending upon delta, the initial position of the oscillating particle is determined. You see, when delta is equal to 0, then at t is equal to 0, x is equal to 0. If delta is equal to pi by 2, then at t is equal to 0, or initially x is equal to a. So the particle begins its motion from the amplitude position. And if you put in some other value of delta, say delta is equal to pi by 4, then at t is equal to 0, you get x is equal to a by root 2. So the initial position then would be a by root 2. So depending upon delta, the initial position is determined. So it is known as the initial phase or epoch. So we have been able to solve the equation of motion of a simple harmonic oscillator and find its resultant displacement. More on this issue in our next lecture. Thank you for paying attention.